So this is third lecture of vectors. Now in this we will start with parallelogram law of vector addition. In last lecture we ended up with triangle law of vector addition. The parallelogram law of vector addition, the statement goes as follows. If two adjacent sides of a parallelogram, if two adjacent sides of a parallelogram represent two co-initial vectors. You can check here, you have a parallelogram. I have drawn a parallelogram. Now, two adjacent sides of a parallelogram. Look at these two adjacent sides, OA and OB. The parallelogram is OACB. Now, these two adjacent sides, OA and OB, they represent two vectors. And these two vectors are starting from same point, they have same initial point. The vector is OA bar and OB bar. Both of these vectors have same initial point O. So they are known as co-initial vectors. They are co-initial vectors. So these two sides OA, OB represent two vectors OA bar and OB bar. So once again, if two adjacent sides of a parallelogram represent two co-initial vectors, then the resultant of these two co-initial vectors, the resultant of these vectors, the resultant of these vectors is given by the diagonal of the parallelogram. The resultant is given by the diagonal of the parallelogram originating from the same co-initial point, originating from same co-initial point, originating from same co-initial point. So how do I give the diagonal? The diagonal will be given by, how do I give the resultant? The resultant is given by the diagonal. See, this diagonal will give you the resultant of OA bar and OB bar. Once again, the resultant of vector OA bar OB bar is given by the diagonal of the parallelogram. Remember, the diagonal also originates from the same co-initial point. Okay, so you have two vectors OA bar OB bar. You have two vectors OA bar OB bar, which are represented by two adjacent sides of a parallelogram. The resultant of these two vectors is given by the diagonal OC bar, which is a diagonal of the same parallelogram originating from same co-initial point. So how do we write it? We will write this as, we will write this as OA bar plus OB bar equals to OC bar. We will write this as OA bar plus OB bar equals to OC bar. This is the parallelogram law of vector addition. In case if you want to prove it, if you want to prove this, you can always do it using the triangle law of vector addition. See, I can prove it, and for proving, I will use the triangle law of vector addition. Now, you can check here that OA bar and BC bar, look at the vector BC bar. OA bar and BC bar, these two vectors are equal vectors. OA bar and BC bar are equal vectors. Why they are equal vectors? They have same direction and they have equal magnitude. You can check OA bar and BC bar. OA bar and BC bar, they have same direction. See, OA bar and BC bar, they have same direction. Not only that, see, it should have come parallel. You have to understand, but then as I drew the rough diagram, it's not coming parallel. See, BC bar and OA bar, they have same direction. Both are having same direction. They are parallel to each other. Not only this, they have same magnitude because they are the opposite sides of a parallelogram. They are the opposite sides of a parallelogram. So what I understand here is, I understand that BC bar is equal to OA bar. BC bar is equal to OA bar. Same way, look at this. OB bar. Look at the vector OB bar. OB bar and OB bar and AC bar. See, both the vectors are in same direction. Both are in this direction, and they also have equal magnitude. So they are also equal vectors. They are equal vectors. So here I write OB bar, I write here AC bar is equal to OB bar. Now I can go for any of the triangles. See, let me go for the triangle OBC. In triangle OBC, in triangle OBC, I'm going in this triangle, right? In triangle OBC, what I notice is, by triangle law of vector addition, by triangle law of vector addition in triangle OBC. See what I have. I will write OB bar plus BC bar plus BC bar. You can check. OB bar plus BC bar is equal to OC bar. It is equal to OC bar. Now you know that the BC bar, you can check. What is BC bar? See, BC bar you have already written. It is equal to OA bar. So you will have OB bar plus OA bar is equal to OC bar. See, you have proved it. You proved the parallelogram law of vector addition using the triangle law of vector addition. OB bar plus OA bar. See, you proved this. OB bar, you proved it. OB bar plus OA bar is equal to OC bar. So after the parallelogram law of vector addition, the next one we are going for is subtraction of two vectors or difference of two vectors. Now when I say difference of two vectors, what do I mean? I simply mean A bar minus B bar, or I mean B bar minus A bar, any one of these two. So what you need to understand here is that how do we get, see, I taught you how to get A bar plus B bar. And A bar plus B bar you understood by triangle law of vector addition and also by parallelogram law of vector addition. When the two vectors are co-initial vectors and you want to add them, you saw here, you saw in this, when the two vectors are co-initial vectors, they are originating from the same point, then you apply parallelogram law of vector addition. And if they are not co-initial, they are like this, like where one vector ends, the other vector starts. If where one vector ends, the other vector starts, you will apply the triangle law of vector addition. So as you have found A bar plus B bar, now it is time we learn A bar minus B bar or B bar minus A bar. Okay, so here in the diagram, I have shown here vector A bar, vector B bar. I have shown here vector A bar and vector B bar. I want to get A bar minus B bar. What I want to get? I want to get A bar minus B bar. Now remember, to get A bar minus B bar, to get A bar minus B bar, you will first have to understand that A bar minus B bar is nothing but A bar plus minus of B bar. What you will have to understand? You will have to understand that A bar minus B bar is same as A bar plus minus of B bar. So you will first find out vector minus B bar. Let us find out vector minus B bar. Where is the vector minus B bar? See, I'll find out vector minus B bar. See, this is vector minus B bar. You have now before you vector minus B bar. Vector minus B bar is, it is a vector, vector minus B bar is a vector which is equal to B bar in magnitude, but opposite in direction, Now this diagram will show you, now I will show you A bar plus b bar. See, what is a bar plus b bar? A bar plus b bar will be this vector. You check this. This vector is a bar plus b bar. It is needless to explain why it is a bar plus b bar. Because you move from this point, see, this is the first point. Okay, you move from this point to this point. This is a bar. Then from second point to third point, this is b bar. So now the resultant is a bar plus b bar. What is this? It is, this vector is a bar plus b bar. A bar plus b bar. A bar plus b bar. This vector is a bar plus b bar. But now check this. If I go this way, I start from here. If I start from here and I move here. So see, what is it now? This vector is a bar. So here, see, 1 to 2, a bar. Now 2 to 4, 2 to 4. This point is fourth point. So 1 to 2, a bar, and 2 to 4 is minus b bar. So what you have? You have a bar plus minus b bar, that is equal to a bar minus b bar. So this vector is a bar minus b bar vector. The vector is a bar minus b bar. So now I have explained that addition of two vectors, as you know, the subtraction of two vectors is also addition. A bar plus b bar, as you know. Now a bar minus b bar is nothing but a bar plus minus of b bar. Okay, what happens is you are adding the opposite vector. A bar minus b bar means you are adding the negative of b bar to a bar. That will get you a bar minus b bar. There are some points to be understood with regard to the addition of two vectors. See, the addition law of vectors can be extended to a polygon. Now here you have a polygon. Here what I'm writing is addition law of vectors. I can extend it to a polygon. Okay, we can extend the addition law of vectors to a polygon. Like we had the triangle law of vector addition, we had the parallelogram law of vector addition. Now we can have a polygon law of vector addition. See, what does it mean? Now here in this diagram, you notice you have a polygon. It has 1, 2, 3, 4, 5, 6, 7. 7 sides it has, right? Now each side is representing a vector. OA bar, OB bar, OC bar, OC, OA bar, I'm sorry, OA bar, AB bar, BC bar, CD bar, DE bar, EF bar, and then here you have OF bar. OF bar is not in the same order, it's in the reverse order. See, the rest of the vectors except this OF, all the vectors are in same order. You can check. They are in same order. You can check. Look at their arrow. They are in same order. But when it comes to OF, OF is in the reverse order. OF is in the reverse order. Now here I want to show you something. Suppose I have here sum of I have OA bar plus AB bar plus BC bar plus CD bar plus DE bar plus EF bar. Okay. Now see, look at this first two. Look at the first two. I have OA bar plus AB bar. So you can check here where the first vector ends. Look at the terminal point of the first vector, point A. OA bar, point A. And look at the next vector, the initial point of the next vector, A. Now where this vector terminates, this vector starts. Where this vector terminates, the other vector starts. So it becomes what? It becomes the triangle law of vector addition. So what is OA bar plus AB bar? This is OB bar. You check this, OB bar. It is equal to OB bar. And then again I will write BC bar plus CD bar plus DE bar plus DE bar plus EF bar. Okay, now and here from the diagram it is very much clear. See, OA bar plus AB bar, OA bar plus AB bar is OB bar. See, I got OB bar here. Now what I want you to understand is, see, now look at these two, OB bar plus BC bar. What will this be? This will be OC bar plus CD bar plus DE bar plus EF bar. Okay, and what will next be? What will this two be? This two will give me OD bar. They will give me OD bar plus DE bar plus EF bar. Now what will these two give me? They will give me OE bar plus EF bar, and finally I'll get OF bar. You check this. So this is polygon law of vector addition. Okay. So you can understand that in this diagram you are applying the polygon law of vector addition. I hope this is clear to you. OA bar plus AB bar. So from you start from point O, you start from this point, okay, you move here, then you move here, then you move here, then here, then here, then here. Ultimately, it is you starting from here and moving here. So that is equal to OF bar. It is the polygon law of vector addition. We have few more points to be taken with regard to addition of the vectors. The first one, the second one here is A bar plus B bar is same as B bar plus A bar. A bar plus B bar plus A bar, they are equal. This is known as vector addition is commutative. The next one is A bar plus B bar, A bar plus B bar plus C bar. A bar plus B bar plus C bar is same as A bar plus B bar plus C bar. It is same as A bar plus B bar plus C bar. What does it mean? It means if you are adding the vectors, the order in which you add, it doesn't make any difference. See, you first add A bar, B bar, then you add C bar to it, or you add B bar, C bar, finally add A bar. It all means the same thing. The vector addition is associative. What does it say? It says that vector addition is associative. Okay, the law of association of vector addition. Then see, A bar plus 0 bar is equal to A bar. When you are adding a 0 vector into any vector, you get the same vector. Okay, addition of 0 vector will not make any change in the vector. Then here you have m and n are two constants, right? So m plus n, they are two constants. They are scalars, they are numbers. So m plus n into A bar, m plus n multiplied to A bar, it is A bar is distributed. See, A bar is distributed. It is distributed. What does that mean? A bar is first multiplied to m, then A bar is multiplied to n. So you get ma bar plus na bar. The next point is if you have a m outside, the sum of, and outside you have m, here you have in the bracket A bar plus B bar, then it is ma bar plus mb bar. The scalar is distributed, ma bar plus mb bar. You can copy this all. The next point, which is very, very, very important point, is position vector of a point. Look at these two words, position vector. It is a vector giving position. I repeat, position vector. It is a vector. I'm talking about, we are going to learn about a vector which is going to give us the position. Position of what? That comes forward. See here, it comes forward here. Position vector of a point with respect to a given point. Okay. So now to understand this, I have a diagram here. Think we have a point here O. Okay, we have a point here O, and in space I have got few more points. Say here I have got point A, I've got point B, point C, point D. Okay, let me have one more point here, and here I have point E. Okay, now see what I do. In order to locate, in order to locate this point in space with respect to origin. I know this origin. The location of origin is known to me. I know where O is. So now if I want to know where this point E is, what I will have to do, I will have to start from point O and go in the direction of E till I reach E. Go in the direction of E and only till I reach E. Don't go ahead. See, this is if I'm going, I'm not getting E. I'm going in the direction of E, but I have moved ahead. This is not done. Okay, I have to only reach to E. Can I stop here? No, because I haven't reached E yet. I need to reach E, and the moment I reach E, I stop. So now this vector here you have, this vector you have, it is known as position vector of point E. See this vector you have, it is known as position vector of point E because it gives you the position of point E. It is position vector of point E with respect to O, and it is written as OE bar. It is written as OE bar. In short, we can also write this as E bar, small e bar. Same way, this vector, this vector is OA bar. This vector is OA bar because it gives us the position of point A with respect to O. This vector is OB bar because it gives us the position of point B with respect to O. This vector here is OC bar. This vector gives us the position of point C with respect to O. See, it's in the direction of point C, and its magnitude is exactly equal to the distance of point C from point O. And finally, here you have vector OD bar. If you want, you can write OA bar. You can write OA bar as simply A bar. This is simply A bar. You can write OB bar as simply B bar, small b bar. You can write OC bar as simply vector C bar, small c bar, and OD bar you can write simply as vector D bar. Okay, so what is position vector? What is position vector of a point from a given point? The position vector of a point from a given point is a vector which gives the position of point with respect to given point. Okay, so here I will write for one position vector. I can write it here. I will write it here. Position vector of point A with respect to point O. Point O. See, here I am taking point O because generally the point with respect to which we find the position vector is origin. Generally, we find the position vector of various points in space with respect to origin. That is why I'm taking origin. Or else, there is no hard and fast rule. You can have with respect to any other point. Instead of P, instead of O, I could have written P. So it would have been PA bar, PE bar, PB bar. It would have been that way. Okay, but we are taking O because generally we always go with respect to origin. So position vector of a point A with respect to point O is a vector is a vector which is which is which is giving the position which is giving the position of point A with respect to O. It is denoted by OA bar or simply A bar. Okay. Mod of OA bar is equal to distance between point O and point A. Okay. So you will write this also. The above diagram shows the position vectors. You can write PVS. Okay, that is allowed. You can write simply PVS. The above diagram shows the PVS position vectors of points A, B, C, D, and E with respect to O. With respect to O.